Alright, y'all, so this particular video is going to be on the general features of nucleophilic substitution. But before we do that, we got to talk about that polar CX bond. And so we've seen it before. We already know that the halogens are more electronegative. They're going to create that polar bond. But as a result of that, we have a site that's susceptible to attack. Let's take a look. We got this alkyl halide with the X and then a nucleophile, right? Then we get something over on this side where that nucleophile is now in the place of that X, and that X came off as an anion. So what kind of reaction is this? We saw it before in the previous chapter, and that is a substitution reaction. So that nucleophile took the place of that X, and that is pretty straightforward in terms of like how that's a substitution reaction. But let me highlight these. I actually I put it we got red and blue. I don't want to swap the red and the blue because I tend to like my electrophiles or my nucleophiles red and my other things blue. So the nucleophile I put as red because I feel like that's like the thing that's attacking, and it should be red because I don't know. That just makes sense to me, right? The hostile thing is red, and then this right here is blue. And notice that the nucleophile substitute that X, and the X left. Bye, Felicia. And that is actually something that we call a leaving group. And this is actually really important. It's the next topic on the topic of the next video. And there's definitely much to talk about these guys, so get ready. Super exciting stuff, right? Yeah. Okay, so let's take a look at another type of reaction that can occur with alpha halides. So again, that bond is polar, and if we have something oriented like this where we have like something called an alpha hydrogen that's on that alpha carbon adjacent to that CX bond and a hydrogen there, right? So we end up with an alkene. What kind of reaction was that? You had something, it left, and then you had an alkene. That was something called an elimination reaction, right? And so I'm highlighting the X in blue, and the B, the base. That's a generic base. Sorry, I want to let you know that. And then highlighting that in red because that's acting as the thing that's doing all the attacking. That's the hostile thing, with the electrons. And so that essentially removes a hydrogen atom, and then allows that X to leave as that leaving group, and then you get the alkene. Okay, and there you have it. So this upper reaction, this is the substitution reaction, and that's this chapter. The elimination reactions are actually next chapter, so sit tight for those. Those ones are a doozy as well, but we gotta get through these nucleophilic substitutions first, right? So essentially we have that nucleophile attacking, like I said, and then the X leaves. And so since that X was a negative charge, we explicitly drew the lone pair. That is a heterolytic cleavage. Okay, so this is really important. So some of the factors that we're looking for when we do a nucleophilic substitution reaction, as it is called, are we need the alkyl group to have a CX bond on an sp3 carbon, sp3 hybridized carbon. We also need a leaving group, and that leaving group is to bear that charge due to homolytic. Okay, I just had to make sure I didn't accidentally put homolytic cleavage on the last part. So then we also need that nucleophile, right? So there's not too many things that are required for this reaction to occur so far. I'll put it at like an exclamation point there, so far. But we got electron-rich species for the nucleophile, and we don't need to have a charge for that nucleophile. Okay, so we got an NH3 versus like an NH2 negative, that ammonia versus the amide. Those are both good nucleophiles. We also have alkenes and alkynes. Those are good nucleophiles as well. They're not negatively charged, right? They are just electron-rich species. Okay, so I just want to point out those are the only three things that we really need for this particular type of reaction. Okay, and so when we're doing these reactions, we want to look for them just to see if they're present, and then now it should be easier to piece them together. So we got this 3-bromopentane with this ethoxide. That is the nucleophile because it's a negatively charged species. It's electron rich. And I'm going to highlight that bromine and the carbon in blue because remember that carbon is bound to an electronegative bromine. That's a delta positive charge, which makes that the electrophile. That electrophile combined with the nucleophile makes this now a Lewis acid base reaction, right? So that's, again, that's all chemistry really is like Lewis acid base chemistry, or oftentimes Bronsted-Lowry acid base chemistry. But as we know, they can be the same thing. So our Lewis acid base chemistry is all encompassing. That nucleophile attacks that carbon that's susceptible to attack because of its positive charge, and then we get a nice little substitution here. So that bromine left, and we've got extra lone pair I've highlighted in blue from that bond because just to show you where it went straight onto that bromine. That's why it has that negative charge. And then the negative alkoxide or ethoxide is now neutral as it has used both of its, or the lone pairs from it, the oxygen, to create that new carbon oxygen bond. And so that's why it's neutral now. So we got this new compound, so this cyclohexane, this chlorocyclohexane with sodium azide. So sodium azide is actually in airbags, and it just so happens to be toxic as well, which is so weird to me. But a bunch of nitrogens together, upon impact, it explodes, and it forms nitrogen gas. So that's why the airbag deploys. And in theory, you shouldn't be exposed to any toxic substances because it is really reactive. And sodium azide shouldn't be present anymore. But anyway, right? So we get this product over here, and then we have a question mark indicating what's there. We had a chlorine there originally. Now what do we want to put there? Well, that chlorine is blue. That's susceptible. That carbon is susceptible to nucleophilic attack by that azide that I've drawn in red because it's electron rich and negatively charged. The sodium plus is just a spectator ion. And we really need to realize that it just balances the charges out. And if we see it as NaN3, we need to know that Na is just a positive charge, and the nucleophile is that N3 only. So that's what we placed there where that question mark was, okay? Now that chlorine is the leaving group, okay? It left, and that's pretty much it. So just to draw the arrows to show you how the flow of electrons work. You got the red arrow going to attack that carbon, and then the bond between the carbon and the chlorine go to the chlorine only. Okay, so this is the nucleophilic substitution product. Obviously the red is the nucleophile, the blue portion is the electrophile. This is also called a substrate. So in nucleophilic substitution reactions, that the alkyl halide is the substrate. Okay, so and then the carbon bound to those halogens is the electrophile that's susceptible to nucleophilic attack. So let's try another one. This is a little bit different. We've got this this alkyl halide with water, which is the nucleophile because it's electron rich, even though it's neutral. We've got that electrophile. Now it's susceptible to nucleophilic attack by that water, and what we initially would get is this particular compound right here plus the chloride ion, right? Now again, that chlorine or chloride is the leaving group, the substrate right there. It's still viewed, when it's on the substrate, it's still viewed as the leaving group. It's just that when it, after on the right side of the reaction, it has left. That leaving group has left. So that's just to make that distinction. It's not just a leaving group on the right side only. Okay. Now back to that nucleophilic substitution product. I've highlighted the water in red because that's came from the nucleophile, but that oxygen is positively charged, and we don't want that to be the case anymore. So we have another water come along, remove that proton to make it neutral. So we get this alcohol as the end product, and that's the final product of a nucleophilic substitution reaction. Okay, that positively charged trivalent oxygen is called an oxonium, and those are always going to be intermediates. We don't usually want to have them live as charged compounds because they're not very stable when they're charged, right? So that's the last kind of like little tidbit of information. Typically, you have the nucleophile attack, and then everything stays on that nucleophile. Whatever was bound to that nucleophile is on there in the nucleophilic substitution product, right? But if it's positively charged or whatever, and you can remove a proton, then you should remove a proton because that's a very simple acid-base reaction that will provide you a more stable compound, being that it is neutral. Okay, so what time do you think it is? You want to talk about practice? Bam! Let's talk about practice. All right. So, we're going to do a couple different types of problems, but they are pretty straightforward. So, what's the product, first of all? And we're obviously assuming this is a nucleophilic substitution reaction. So, we have an alkyl halide and we have an amine here. So, really, what you want, remember, you want that sp3 carbon with a halogen on it, and you want a nucleophile, and you are looking for a leaving group, which is that halogen. So we label our nucleophile, we label our electrophile and our leaving group, and then we pretty much jam the two together and make the leaving group leave. Again, bye Felicia. See you later. And no, you can't borrow my VCR. Anyway, teehee. We got that nitrogen coming in, and it is just taking the place of that bromine, and that's pretty much it for the nucleophilic substitution product, right? So this is the other type of problem. I want to draw the substrate or the electrophile, alkyl halide, and then I'll draw the product of a nucleophilic substitution reaction, and I want you to tell me what the nucleophile was, what it is, what it isn't. So let's labeling in blue our electrophile. Labeling in blue what the electrophile, what's left of the electrophile on the right side. So what does that leave? Remember, that chlorine left. That was a leaving group. That leaves only the rest of this molecule on the left, which would be a nucleophile. If we were to cleave that bond between the nitrogen and the blue carbon, we could see that we would end up with an amine with a lone pair on it, and that is a great nucleophile. We've definitely seen amine nucleophiles before, right? So that would attack that carbon, that chlorine would leave, and we would get an intermediate compound. That's a tetrahedral intermediate. We got 4 bonds of that nitrogen. It's positively charged, and we don't want that. So a generic base B is written to remove that proton, and we get the final product on the upper right. Okay, so this step right here, where we're removing that proton to neutralize it, that's called a proton transfer. Okay, so you need to know that term just so that when we're talking about it, we could just say a proton transfer occurs and we get that neutral product. Yay. Okay, so that's pretty much it for substitution reactions. I mean, that is very, 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 very straightforward when it comes to nucleophilic substitution reactions. Because now we need to talk about different conditions. So we're going to talk about leaving groups and how they affect the rate of the reaction or the products or whatever. Then we're going to talk about stereochemistry and nucleophiles more specifically. And it's about to get crazy, but it's going to be super fun because it's the ultimate puzzle. And yeah, so have fun with it and just do your best. Try and get the practice in for sure. It's all about repetition here. First time you rode a bike, you probably fell down. Okay, you didn't just start cruising the beaches like after 2 times, right? You got to put in that work. Okay, so back at it again with those dad jokes. All right, so dad jokes 101. I'm not sure if you knew this, but you don't actually need a parachute to go skydiving now. Yeah. You only need a parachute to go skydiving twice. Ah. So good.